So this video is still on the course of representation theory. We are still on the chapter of group representation. So this video begins with this proposition, begins and ends, because I'm going to give a proof for this. With this proposition, let phi be a representation from the group G to the general linear group. But this representation is unitary. Okay, so let phi be a unitary representation of a group. Please check the previous video for unitary representations. So if phi is a unitary representation, then phi is either irreducible or decomposable. Okay, and I'm going to provide a proof for this. Okay, so the theorem says phi is either irreducible or decomposable. So what you're going to do is, let us say that phi is irreducible. So if phi is irreducible, if everything goes well, I will end up proving that phi is decomposable. Okay, so without loss of generality, let us say that phi is irreducible. Okay, so if phi is irreducible, there is a non-zero G invariant subspace W of what is the space here? Okay, I'm going to say U. Okay, I'm calling it U because this is a unitary representation. Okay, so this is the subspace, right? Do not forget that we agreed that we are going to use this notation for subspace. Okay, so this is a subspace, and this will be the orthogonal complement, right? So this will be the orthogonal complement. Okay. So vector, what is the vector here? Vector v. So v, just follow linear algebra, can be decomposed into the subspace W, direct sum with the orthogonal complement. Okay, so now we have to prove that the orthogonal complement is G invariant. Okay, if we prove this, we are okay. Because if we prove that the orthogonal complement is G invariant, V can be decomposed into W and its complement. Okay, so phi is decomposable. Okay, so if phi is irreducible, then phi is decomposable. Okay, but we still have to prove, okay, W is guaranteed, right? Because it's a subspace of U. Okay, W is guaranteed. The thing is, we still have to prove that the orthogonal complement is G invariant. Okay, so I can write the inner product of phi G of V, inner product with W. Why can I say this? Well, do not forget that phi is unitary, right? So I can write the inner product between an image of V and W, where obviously I did not write it here. So I'm going to say that, I'm sorry, I did not write here, that V, I'm going to say that V is in the orthogonal complement, and W is in W. Okay? Okay, so we want to prove that the orthogonal complement is G invariant. So, okay, so I start with the inner product, right? I can write the inner product because phi, do not forget the proposition says let phi be a unitary representation. Okay. Okay, so phi is unitary. Now I can write this and this. I can, at the end of the day, I'm left multiplying, right? Why is that? Because this equals the identity, right? So I can write on the inner product. This is one of the properties of inner products, right? I can write this. Now, if you look well, this one, phi G inverse W. So phi G inverse W is in W, is here, right? And W is G invariant, okay? Okay, and V, where is V? V is here, and V is in the orthogonal complement. So phi inverse, so this phi G inverse phi G of V equals V. Okay, here you are. Okay. I have something wrong here. This should be this G, right? So this V here is in W, right? And this one, this phi of G inverse W, has to be in the inverse image of W has to be in W. So wrong. This V here cannot be in W. This V is in the orthogonal complement. Okay, so this is equals 0. So phi is decomposable. So phi is decomposable, and that concludes the proof. So if phi is a unitary representation of a group, then phi is either irreducible or decomposable. And our proof began assuming that phi is irreducible. But since phi is irreducible, we got to the conclusion that phi was decomposable.